You know what I mean around people? It's weird. Never experienced it that empty.
That's it, like every day.
Yeah.
Well, I know kids.
Very different upbringings. Okay, so let's really quick start by recapping what I did last time. Again, this isn't the way that the author does it. We'll do the way I like to do it, we'll do the way the author does it, and then we'll do some, just some more stuff. The author, I really hate how the author handles this section. He only does one theorem in the whole section that he actually proves. The rest he expects the students to just figure out, which is terrible. And so we'll prove the one theorem that he proves. Split into two so it's more consumable. Anyways, let's just start. So we already proved this at the end of last week. We just didn't have it recorded, so we'll restart here. Let P be a prime number and let A be any integer such that P does not divide A. With me so far? Then we're saying A to the P minus 1, P is a prime. A to the P minus 1 is congruent to 1 mod P. Is this ringing bells? Remember doing this? You remember what this means? They have the same remainder when you divide by P?
Yeah.
Okay. Or their difference is divisible by P. Is another way to think about that. Okay, so consider the first P minus 1 multiples of A. That's 1 times A, 2 times A, 3 times A, 4 times A, 5 times A, all the way up to P minus 1 times A. So we're looking at this list of multiples of A. Good? Okay. Assume, by way of contradiction, that two of the above factors are congruent mod P. So assume that I can find two things in this list that are congruent mod P. Assume by way of contradiction. I'm going to show that this is impossible. So in other words, this number mod P is different from this number mod P, is different from this number mod P, etc. That's what I'm going to prove. So assume by way of contradiction that two of these numbers are actually the same mod P. That is, I can find two coefficients, R and S, such that R times A is congruent to S times A mod P, where R and S are between 1 and P minus 1, and they're not the same number. With me so far? Yeah. I'm going to show that this being the case leads to R and S being the same number, contradiction. Okay, so then, since we're assuming that R times A is congruent to S times A mod P, that's the same thing as P divides our difference, right?
Yeah.
Why is that?
That's the definition of this. A is congruent to B mod N if and only if N divides their difference. That was our definition of modular equivalence. Is that ringing bells?
Yep.
Okay. So we're good with this line? Okay. So now R times A minus S times A, I'm just going to factor the A out. Good? So now we have P, a prime, divides a product of two numbers. Now we proved, I think this was even on your last test, that if P divides a product of two numbers, then P divides the first number or P divides the second number, right? So I know P divides A or P divides R minus S. But by assumption, P does not divide A. So P has to divide R minus S.
Yeah.
Okay. So that means if P divides R minus S, that's the exact same thing as R congruent to S mod P, right? Second theorem that we use all the time and forever, R is congruent to S mod P is the exact same thing as R mod P equals S mod P.
Yeah.
In other words, R and S, when you divide it by P, give the exact same remainder. But notice that R and S are numbers between 1 and P. So what is R mod P?
It'd be R.
It's just R. If I say, what's the remainder of 9 when I divide it by 52, what is it?
9.
It's just 9, because that's a number smaller than 52. 52 doesn't even go into it once. R and S are numbers between 1 and P minus 1, which is also less than P. So their remainder when you divide by P is just whatever those numbers are. So R mod P is R and S mod P is S. So R is equal to S. Contradiction. You follow that?
Yeah.
Okay. So therefore the list of factors A is congruent to 1, 2, 3, all the way up to P minus 1 in some order. What does that mean? So let's go back. I know that First off, how many numbers do I have listed here? How many numbers are in this list? Not A of them.
P or P?
Not P.
One.
P minus one of them. There's 1, 2, 3, 4, 5, 6, 7. P minus 1. That's how many numbers are in this list. You with me?
Yeah.
And I also know that when I mod it by P, no two of these numbers are the same.
Yeah.
So when I take a number and I mod it by P, how many possible numbers can it spit out?
P minus 1.
It can spit out P possible numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to P minus 1.
Yeah.
Now, we know that none of these are 0. How do I know that none of these are 0? With 0, sorry, I'm saying 0, but how do I know that none of these are of this form? Some number, what should we call the number? K times A is congruent to 0 mod P. How do I know that none of these numbers are congruent to 0 mod P? If one of them was congruent to 0 mod P, that would be the same thing as P divides K times A minus 0, or just K times A, right? How do I know that this is impossible?
P can't divide A.
P can't divide A, but why can't P divide K? Why can't P divide 1, or P divide 2, or P divide 3, or P divide 4, or P divide P minus 1?
Because it's a prime.
Because P is a prime, and those are all numbers less than that prime number. Right? What's the smallest number P can go into?
Itself.
P itself. So it can't go into any number smaller than it. So all these numbers right here are, when I mod them by P, are going to spit out the numbers 1, 2, 3, 4, 5, 6, all the way up to P minus 1. Now I have no clue what order they're going to do that in. This one, when I mod it by P, might give me 3. This one might give me 5. This one might give me 1. Dot, 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 dot. But when I mod them all by P and I look at all the numbers that they give me, it's going to give me the numbers 1, 2, 3, 4, 5, all the way up to P minus 1. Just in some order. I don't know what order. You with me? Okay, that is what I'm saying right here. So therefore, the list of factors of A, this list, is congruent to 1, 2, 3, all the way up to P minus 1 in some order. It's possible for me to rearrange this so that when I take the mod of these, it gives me these numbers. You follow that thinking? Wonderful. Okay. So then, if all these numbers are the same as all these numbers, mod P, then if I multiply them all together, then I'm multiplying the exact same numbers together, mod P. So then I'm saying, that means that 1 times 2 times 3 times dot 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 times P minus 1 is congruent to 1A times 2A times 3A times 4A times dot 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 times P minus 1A. Because they're the same list of numbers, just in a different order. Right? If I take two lists of numbers that have the exact same numbers in it, but in different orders, I multiply them together, I have the same numbers, right?
Yeah.
So that's what we're doing here. So then, this list multiplied together, 1 times 2 times 3 times all the way up to P minus 1, is congruent to A times 2A times 3A all the way up to P minus 1A. You follow me up to this line?
Yeah.
Okay, this is just rewriting this. What is 1 times 2 times 3 times 4 all the way up to P minus 1? That's just P minus 1 factorial. Good? Similarly, what is A times 2A times 3A times 4A all the way up to P minus 1A?
P minus 1A.
It's P minus 1 factorial times A to the P minus 1. How did I mess that up? This is P minus 1, right? There's only P minus 1A, so we're multiplying together. Which means I mess this up. P minus 1. Which means I mess this up. P minus 1. Which means I mess this up. P minus 1. Which is what we were trying to prove. Right? P minus 1. Okay. Should have caught that earlier. Anyways, so multiplying all these terms together just gives me these two terms.
Yeah.
You see that? Okay. Now, I know that this is congruent to this mod P. Sorry, I didn't write my mod P here. But it's a congruence mod P, which means P divides their difference. So P divides this thing minus this thing, right? And I'm just going to factor this term out of the difference. So when I factor this out of it, then I'm left with 1 minus a to the p minus 1. You see the algebra there?
Yeah.
Another way to see it, if you're missing the algebra, let me rewrite that. Parenthesis comes down, that's an arrow. Redistribute. If I distribute that through, then I get p minus 1 factorial minus p minus 1 factorial times a to the p minus 1, which are the two terms you have here. Anyways, so p divides this product. What does that mean? P is a prime. It divides the product of two numbers. This is just an integer. This is just an integer. Whatever it is. Who knows? Doesn't matter. The point is,
It divides one or the
it
other.
has to divide one of those two. Now, why do I know that P does not divide this thing?
Because it's less than. Because p minus 1 is less than p.
This is P minus 1 factorial. So if P is 7 here, then this is 1 times 2 times 3 times 4 times 5 times 6. How do I know that 1 times 2 times 3 times 4 times 5 times 6, that 7 does not divide that? This number has a unique prime factorization. Right?
Yeah. It's had to be.
Let's look at it in the case of 2 times 3 times 4 times 5 times 6. Well, first off, what is 2 times 3 times 4 times 5 times 6? What's 1 times 2 times 3 times 4 times 5 times 6?
720.
720, wonderful. So 6 factorial is equal to 720. Now how do I know right out the door that 7 does not divide 720? What is the prime factorization of this thing? How many 2's does it have? 720 is equal to, it's equal to 6 times 5 times 4 times 3 times 2, which is equal to, okay, how many 2's do we have? We have 1, 2, 3, 4 2's, times how many 3's do we have? 2 3's, 1 here, 1 here, and then how many 5's do we have? 1. Right?
Mm-hmm.
This is the same thing as 2 times 3 times 4 times 5 times 6. Do you see how I did that?
Yeah.
You can break 6 up into 2 and 3. You can break 4 up into 2 and 2. And there you go. How many 2's do we have? 1, 2, 3, 4. How many 3's do we have? 1, 2. How many 5's do we have? 1. Here's its prime factorization. 7 is never going to be in its prime factorization. Because it's only multiplying together numbers smaller than 7. And numbers smaller than 7 are going to have a prime factorization of prime smaller than they are, so smaller than P. Make sense?
Yeah.
Okay, so we know P does not divide this. P has to divide one of those two, therefore P divides this. Good?
Okay.
Rewriting that, that's the same thing as 1's congruent to a to the p minus 1 mod P. And we're done.
Yeah.
Okay, this was not Fermat's little theorem that the book says. That's going to be a quick corollary of this. Here's what the book proves. So let's do what the book proves. Let a be any integer and p be a prime, then a to the p is congruent to a mod p. Slightly different. What did we say? Let p be a prime and let a be an integer such that p does not divide a, then a to the p minus 1 is congruent to 1 mod p. So slightly different. Okay, so let's prove this. Well, we have two cases. If a is any integer, we have two cases. Either p divides a or p doesn't divide a. Those are the only possible cases, right?
Yeah.
So if p divides a, then what is a mod p?
A.
A.
Now, if p goes into a an even number of times, what is a mod p? For those of you in computer science, what is 40 mod 4?
0.
0. How did you know that?
There's no remainder.
Because there's no remainder, or in other words, 4 is a factor of 40. Let's say this again. If p is a factor of a, What is A mod P?
0.
0. So if P divides A, then A to the P is congruent to A mod P because they're both just congruent to 0. A is 0, 0 to the P is still 0, 0 is congruent to 0. Okay, so that case is trivial. Everyone good with this case? Alright, next case is more interesting. Okay, let's look at the case that P doesn't divide A. Well, we know from our previous theorem that A to the P minus 1 is congruent to 1 mod P. Multiply both sides by A.
Oh, yeah.
Simple proof.
Yeah, simple corollary from our previous proof. Okay, so this right here is Fermat's little theorem. That's what it's called. This is the only proof, new proof, that the author gives you in the whole section, unfortunately.
The corollary?
The proof of this thing. I split it up like this. I prove this, then this. The author just proves this directly. Now we're going to go over one of the author's way of proving it. No, he never proves this. He just proves this. Which is too bad, because this is a very interesting result, and we'll see why at the end. Now we'll go over the author's way of proving, one of the author's way. The author gave you 3 proofs. Pick any one that makes the most sense to you, and do it that way. I'm going to do proof by induction. And I broke up into 2 proofs. The author combines these 2 into 1, but I think combining into 2 helps you follow pieces in your head. Okay, so now we're going to prove that A to the B is congruent to A mod P, where A is any natural number, not any integer. We're going to start with the natural numbers and handle the integers in our next proof. So we're going to limit ourselves to just the natural numbers here and P sub prime. So prove it for the special case of the naturals. And we're going to do proof by induction. Alright, let P be a prime base case. When A is equal to 0, oh, I start with 1. 0 is trivial. So base case with 0, let's make sure we see 0 real quick. 0 to the P is congruent to 0 mod P, always and forever.
Yeah.
Okay, so 0 should be our base case, but actually I'm going to start with 1, so now we'll look at 1. Well, what's 1 to the P? 1 to the P is still just equal to 1, so 1 to the P is congruent to 1 mod P because it's the exact same thing on both sides.
Yeah.
Okay, that's our base case. Now assume for A equal to K that K to the P is congruent to K mod P. And we're going to show that it's true when A is equal to K plus 1. And then we're done. Assume it's true for K, show that implies it's true for K plus 1. Proof by induction.
Why do you have to change it to K?
You know, I'm just doing it how you're used to doing it. You're used to seeing an N for A, but it's typical that you replace it with K's and then do K plus 1 in your next one. So I just did that because I thought that would make it easier for you to follow.
Yeah,
Okay, so assume that when A is equal to some integer K, or some natural number K, then K to the P is congruent to K mod P. What is it our job to do? Our job is to show that K to the K plus 1 to the P is congruent to right here. Here's what we're trying to ultimately show. K to the P plus 1 is congruent to, nope, that's combining it all in one go. I'm trying to show that this is congruent to this mod P. And then we're done if I can show that. Right?
Okay.
So then K plus 1 to the P, binomial theorem. Remember binomial theorem? How to expand this thing out? Yeah? Well, if Leah does, then you all do for sure. So let's just write it out. K plus 1 to the P is equal to the sum from I equals 0 to P of P choose I times K to the I times 1 to the P minus I. Yeah?
Yeah.
You follow that? Make sure you see where all the terms are. Here's the 2 things that we have in here. So we have a K and a 1. Those are the terms showing up right there. I iterates from 0 to P. So one of them is going to be to the I, one of them is going to be to the P minus I. And then that's just P choose I. And then in case that notation, oh, I wanted to simplify it once really quick. What's 1 to the P minus I? 1. 1 to the anything is just 1. So quick simplification gives us this. Good?
Okay.
Now expand this out in case you didn't have intuition for what that was to begin with. That's the same thing as p choose 0 times k to the 0 plus p choose 1 times k to the 1 plus p choose 2 times k to the 2 all the way up to p choose p times k to the p, right?
Yeah.
We're just adding up all the terms that this gives us when we plug in 0 for 1, or 0 for I, then 1 for I, then 2 for I, all the way up to plugging in p for I. So that gives us this. Okay. Oh, I didn't make this note really quick. Let me make this note really quick. What's p choose 0?
1.
1. What's k to the 0?
1.
So this is 1. What's p choose p?
P 2.
How many ways can I choose 10 objects out of a bag with 10 objects in it?
10.
1. There's only one way. Take everything.
Okay.
How many ways can you choose p objects from a set with p elements? 1. Take all of them. So this is 1. And what's k to the p?
1. K to the P.
No, it's k to the p. So this whole thing right here is just k to the p.
You guys are messing with that.
So we have 1 plus a bunch of stuff plus k to the p. You with me?
Does that whole bunch of stuff not matter?
That whole bunch of stuff turns out is not going to matter. So in short, what we're going to end up with, I'll write it down here, we're going to end up with 1 plus k to the p is congruent to 1 plus k to the p, like that. And then since I know k to the p is already congruent to k by assumption, then this is going to be congruent to 1 plus k, and we'll be done.
Okay.
Okay.
That's where we're going with this. So my job from here on out is to show that all these middle terms, not counting these two, all the other terms give us nothing. They give us 0 mod p. That's what we're going to be showing from here on out. You with me? And how do we show that they give us 0 mod p? I show that p divides them. If they're divisible by p, then the remainder when you divide by p is 0. So I'm going to show that p divides all those middle terms. Okay?
Okay.
So observe that for I between 0 and p, not including 0, not including p. So we're talking about only the middle terms now.
Yeah.
Then this p to the I, our formula for writing this is this, p factorial over p minus I factorial times I factorial, right? Now since I can't be 0 and I can't be p, then this term right here cannot be p factorial, and this term right here cannot be p factorial.
Yeah.
This has to be smaller than p factorial, and this has to be smaller than p factorial.
Yeah.
You're good? So what does that mean? That means that we're going to have a p in the numerator that doesn't get canceled out in the denominator.
Wait, what?
Yeah.
You're saying,
So
you said that I is between 0 and P, so yeah, it's not going to be bigger than P, but then you're saying,
I can't be 0, so this can't be p factorial.
yes.
And I can't be p, so this can't be p factorial.
Yeah.
You with me there?
Yes.
Okay. So when I take a p out of the numerator, then now my numerator is p minus 1 factorial. And now look at the denominator. The biggest that this one can be is p minus 1 factorial. From there on out, it can only get smaller. P minus 2 factorial, p minus 3 factorial, p minus 4 factorial, right? It can't ever get up to p.
Yeah.
This can't ever get up to p.
Right.
So these cannot cancel out this p in the numerator.
Yeah.
So p is a factor of whatever this whole integer is.
Okay.
Notice that if I was allowed to be 0, then we couldn't say that. Because then you have a p term down here.
Yeah, you can cancel that.
If I could have been p, then you can't say that, because then you have a p term down here. It's only when you make sure that I can't be 0 and I can't be p, that it's true that neither of these terms can cancel out my p in the numerator. So whatever this integer is, who knows, we know that it has a factor of p. So p always divides p choose I as long as I is between 0 and p, not including 0, not including p. So each of those terms, p choose I, is congruent to 0 mod p. So all those middle terms go to 0. So then k plus 1 to the p is congruent to 1 plus a 0 term plus a 0 term plus a 0 term plus a 0 term plus k to the p. All those 0 terms go out, and we're left with 1 plus k to the p. Now I know by assumption, assume for a equal to k that assume k to the p is congruent to k. So I have 1 plus k to the p. So I have 1, or k plus 1 to the p is congruent to 1 plus k to the p. So far, right? But I know k to the p is the same thing as k by assumption. So since k to the p is congruent to k mod p, then I want to put this one back there so you can see the whole thing come together. K plus 1 to the p is congruent to k plus 1 mod p. Because this is congruent to this, and this is congruent to this.
Makes sense.
Therefore, so that's our proof by induction. We showed our inductive step, and therefore a to the p is congruent to a mod p for any natural number a. And that just handles the natural numbers. Now we got to prove it for the integers. Right? Because the theorem's about any integer, not just the natural numbers. So, quick follow-up proof. Now, let a be any integer and p be any prime. We're just going to show that a to the p is congruent to a mod p from Ma's little theorem. Same exact thing we showed over here. Let a be an integer and let p be a prime. We have two cases. Either a is a natural number or it's not a natural number, right?
Yeah.
If a is a natural number, then we're done. We just proved that. So now let's say that a is not a natural number. Now if a is not a natural number, what kind of number is it? It's a negative integer, right? And what is the negative of a negative number? A natural. So if a isn't a natural number, negative a is a natural number. So just because we're talking about negative a does not mean we're talking about a negative number. Because we're talking about the negative of a negative, which gets us back to positive. Okay? So if a is not in n, then negative a is in n. Right? And so, negative a to the p is congruent to negative a mod p, because negative a is a natural number. And we already know this is always true for any natural number.
Yeah.
With me? Now we have two cases here. Notice that p is a prime number. If p is odd, then what is negative a to the p? That's the same thing as negative a to the p, right? Because we have an odd number of negatives.
Yeah.
Yeah.
So when p is an odd number, then we get a to the p is congruent to negative a, times both sides by negative 1 gives me a to the p is congruent to a, and we're done. So that one's going to be easy. The weird case is we got to worry about when p is 2, because 2 is a prime, but 2 is even. So we'll handle the 2 case and then come back and talk about the odd case again. So if p is 2, then negative a squared is the same thing as a squared, right?
Yeah.
Okay, and then a squared is congruent to a. How do I know that?
Because you're
Is your mod by 2? Oh no, that's not one. A squared is equal to a. Oh, it's because of the
you didn't
The
we
thing.
just prove that? Yeah.
a to the 2 is congruent to a
Mod p.
mod 2.
A to the 2 is congruent to a mod 2.
Yeah. Because it's a natural number.
No, negative a is the natural. So I think I'm doing this group. Negative a is a natural number. Am I doing this right?
No, it looks like you're doing it right.
Negative a is my natural number. So I know that negative a is congruent negative a, and it's also congruent to a squared, and then I know negative a is always congruent to a squared. Hold on. I don't like something about what I'm doing, and I can't place my finger on it. P is equal to 2, the negative a squared is the same thing as a squared. Yes. Is a squared congruent to a? How do I justify that one? Alright, I don't know how I was thinking I was justifying it, so let's just come up with a way to justify this real quick. When we mod 2, what does it give us? It gives us the parity of the number. Even or odd. Right? 1 if it's odd, 2 if it's even. Okay, so really quick, if a is even, then an even squared is even. And if a is odd, then an odd squared is an odd squared is odd. An odd times an odd is an odd. First we did, way back. An even times an even is an even. An odd times an odd is an odd. So a and a squared have the same parity. So they're congruent mod 2. So that's how I'll justify going from a squared to a. I'm not sure what I was thinking. I probably had an easier way to say it. But that way works. And then a and negative a always have the same parity. Pretty sure that's something that we proved, but
Yeah.
easy enough to justify again. But the short of it is, okay, now we have negative a to the prime is congruent to negative a mod 2, which is what we were after. Okay, otherwise, if p is odd, then negative a to the p is congruent to negative a to the p, which is congruent to negative a mod p. Which gives us that a to the p is congruent to a mod p. Because we multiply both sides by negative, like I said before. So we show that in either case, a to the p is congruent to a mod p, no matter what. We had it here when p was a prime and a was negative, p was an odd prime and a was negative. We had it here when our prime was 2 and a was negative, and then we had it here when a wasn't negative and p was prime. So in all 3 cases, it was true. Therefore, it's always true. Good? Okay, so now let's have a quick change of gears for the stuff the author didn't do, but a theorem that he ultimately shows you that he expected you to just figure out on your own. Before we do, let's throw out a quick definition. This right here, this function right here is called Eulers Totient. What does it give us? It gives us the number of elements in Zn star. So let's remind ourselves about what is, maybe start with Zn real quick. What is Zn? What's Z10?
It's all numbers from 0 to 9.
0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What's Z10 star?
Prime. It's all the ones relatively prime.
Yeah.
Yeah, it's all the numbers from 0 to 9 that are relatively prime with 10. What does it mean to be relatively prime with 10?
They share one common greatest common.
Their GCD is 1. Their greatest common divisor is 1. That's the only thing that goes into both of them. Alright, so let's make sure you understand this real quick. So what's Eulers Totient of 6?
0, 1,
Not 0.
1, 4.
4 is not relatively prime with 6.
2.
They have a common factor of 2.
1 and 5.
1 and 5.
So 2.
1 and 5. 2. Alright, what about for 12?
1, 5,
7, 9,
7, 9,
no,
11. 4.
4. Alright, 13.
12.
12. Look at that.
In the turn, did you know ISO 13?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 is prime. Its only common divisors are 1 in itself. What about 17?
16.
16. Alright, you're seeing a lovely pattern. It's really easy to figure out what that number is when it's prime. Right?
Yeah.
So now let's do a quick little theorem. We're going to prove something a little bit more general than what you were saying. So you're saying that Eulers Totient of P is equal to P minus 1 when it's a prime, right?
Yeah.
So that could be a proof. That's going to be a quick corollary of what we're going to prove. We're going to prove something slightly more general. If P is a prime and K is any positive integer, then P to the K is equal to P to the K minus P to the K minus 1.
Isn't that just P?
Why did they make it so complicated?
We're
Isn't that
doing
just-
this one because it's a slightly more, let's do the
Isn't
special
it
case
just
that you just
one?
talked about. The special case that you're talking about is when K is equal to 1. That's one that we did here. When K is equal to 1, then we said phi of P to the 1 is just P, is equal to P to the 1 minus P to the 0.
You're right.
So this is a special case of this where K is 0.
Yeah, I see.
So we probably could have done a proof of this with proof by induction. I don't know.
Wouldn't it P to the K minus P to the K minus 1 is P1?
Whoa, 2 to the 5 minus 2 to the 4 is not 1.
Oh, yeah, I see that weird.
7 to the 5 minus 7 to the 4 is a very massive number.
Yeah.
Yes. Okay, so no, this is definitely not 1. And for, depending on what your K and P are, it can easily be a very massive number. Alright,
Isn't it just P? It's not P.
is 2 to the 5 minus 2 to the 4 equal to 2? Is 32 minus 16 2?
No.
No. Let's try another one. Let's look at 3 to the 4 minus 3 to the 3. Is 81 minus 27 3?
81.
81 minus 27.
Oh gosh.
Is that 3? No. Just trying to say no how my little daughter does. No.
She's probably telling us that. Something about that.
Yeah, she toys with me. She has a little puzzle where she has to put the numbers in. And 6 can go in both the 9 and the 6th position. So she'll take the one that's a 9 and she'll stick it in the 6th position, look at me and go, no. And then move it over to the 9. Because it's color coded so you can tell which one goes where. Anyways, let P be prime and let K be a positive integer. Now, what are we looking for? We are saying how many integers clear up to P to the K, so 1, 2, 3, 4, all the way up to P to the K, are relatively prime with P to the K, right? That's the question we're trying to answer.
Yeah.
Here's the way that we're going to do it. First off, how many integers are there from 1 all the way up to P to the K?
P
P to the K minus 1.
There's P to the K, including P to the K.
Oh.
So going 1, 2, 3, 4, all the way up to P to the K, there's P to the K of those, right? So we're going to look at all P to the K of those, and we're going to subtract away all the ones that have a common divisor with this. That isn't 1. So then we're going to subtract away all the numbers that have a common factor with this. Now, what does a number look like if it's going to have a common factor with this? It has to have a P in it, right?
Yeah.
So it has to be a multiple of P.
Yeah.
So it either has to be, if it's going to be a multiple of P, it either has to be 1 times P, or it has to be 2 times P, or it has to be 3 times P, or it has to be ... P to the K minus 1 times P. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to P to the K minus 1 times P. These are all the multiples of P between 1 and P to the K. Notice that this is P to the K. So we're going to subtract away all the multiples of P, and what we're left with are all the ones that weren't a multiple of P. Right? And how many of these multiples of P are there?
P to
Not
the
1, not 2, not 3, but
K minus 1.
P to the K minus 1 of them. So we're going to subtract away those P to the K minus 1 of them. And that's all we're doing here. So observe that the GCD of some number and p to the k equals 1 if and only if p doesn't divide that number.
Yeah.
Observe that there are p to the k minus 1 integers between 1 and p to the k such that p divides the integer. Namely, 1 times p, 2 times p, 3 times p, 4 times p, all the way up to p to the k minus 1 times p. All the multiples of p between those are going to be all the numbers between those that p divides, right? Therefore, there are p to the k minus 1 integers p divides, which means that there are p to the k minus p to the k minus 1 integers p does not divide. Therefore, all the numbers relatively prime with this number, from 1 to this number, there's that many of them.
How would you use that to solve a problem? Yeah.
How would you use this to solve a problem?
Solve those up there. You can't, because there's no k's.
So, I don't know. I'm trying not to go over there because I don't know I have room. Let me just point this over some so that we get it on here. I have some work over here. So now I ask you, okay, what is something like anyone?
What is
Can
that?
you spit it out?
What is that circle thing called again?
Eulers Totient.
It'd be
This one's really easy, even if you don't think about it this way.
63?
No.
It's
12.
No.
60. 36.
32. How'd you get 32? It's even! You just remove all the evens. All the odds are going to be relatively prime. Because what is this? This is 2 to the 6. So, it's only going to share common divisors with evens, so get rid of all the odds. Or get rid of all the evens, and you're left with the odds. How many odds are there between 1 and 64? 32, half of them. Now we could have also called this is going to be 2 to the 6 minus 2 to the 5, which is equal to 64 minus 32, which is 32.
Okay, wait. Now, do not.
Should we do another one? Let's do phi of what? 81.
You have to split it up into the. Oh, you have to get a prime number right there.
Yeah, I'm giving you very special numbers here.
9. Just kidding.
38.
Huh?
Nothing.
3?
Yeah, it'd be 3 to 4.
60.
Yes, it. That's
Almost.
2, 4 minus. It's
Oh,
81 minus 27.
54.
54. Yeah, 81 minus 27 equals 54.
Okay, can you please explain to me
Yeah.
how?
43.
3 to the power of 4.
3 goes into 81, honey.
That's so complicated.
What was complicated?
Trying to figure out the 3 to the 4.
He's wondering.
Oh, that's what you're stuck on.
You just do a prime factorization.
That's 9 times 9. Or 3 times 3 times 3 times 3.
That's true.
Yeah, that's how math works.
Oh,
Alright, should we try another one?
Yeah.
Alright, we'll pull out one then.
Five, 1, 2.
Good job! 512.
That was so hard.
What did she do? She guessed that that's got to be a multiple of 2, so get rid of all the evens. Good job.
You'll do an odd one that's hard.
Yeah.
Hey, that's just divisible by 5.
Yeah, that's
Is that right, Ron?
no.
No. I just am a little bit confused. 625 divided by 5 is 125.
Okay.
Just so you guys know.
500.
That doesn't make
500.
sense.
Yep.
How did you do that?
This is 5 to the 4, or 625, minus 5 to the 3, or 125.
Right on.
You even found out that this was 125. So 625 minus 125 gives you,
Oh, so I did it right.
Yeah.
well, no, you didn't do it right. You just spat out useful information. You don't get credit because you randomly said something and it showed up in the end.
No.
So that's how it's useful. And then there's a cool extra theorem of this, which we won't prove, but that is that Eulers Totient for the product of two primes, p and q, where p and q are primes, is equal to p minus 1 times q minus 1. So you can do it for a product of primes now. And then you can expand that out. You can combine that with that to start doing it for any prime factorization. And so you can start hacking it for very big numbers. Anyways, let's get to this theorem now. Last thing the author gives you, but doesn't really give a good proof of. Let n be a positive integer. This is, I can't remember what, I think it's just called Eulers theorem. But it's a generalized version. It's often referred to as a generalized version of Fermat's little theorem. So this is supposed to be more general than Fermat, and we'll make that connection. We're not going to prove this, but we'll show you the connection. So let n be a positive integer and let a be any integer, such that the GCD of a and n is equal to 1. So a and n are relatively prime. Then a to Eulers quotient of n, totient, not quotient, of n is congruent to 1 mod n. Now notice in the special case where you pick n to be a prime number, then a to Eulers totient of n is the same thing as a to the n minus 1, right?
Yeah.
So this then says in the special case where you pick n to be a prime, you get a to the n minus 1 is congruent to 1 mod n.
Which is the same thing as
Right, if you pick n's a prime. So you can replace n with p if you want, which is exactly what we showed over here. And then you see how, obviously, Fermat's little theorem follows immediately from that as corollary. So that's why this is often referred to as a more generalized version of Fermat's little theorem. Because we're not limiting ourselves now to just talking about primes. So we didn't prove this. Proving this isn't trivial. We have to do a few more proofs in between to work our way up to proving this. So sorry, I just have to leave you with the fact that it's something that's proved and that we can use. And I just wanted to help you get comfortable with what this function was. Because it shows up a lot. Alright. So that's the end of discrete math for material that we'll be covering. There you go. We'll do
Wait, forever?
forever and ever,
Forever?
unless you guys want to do like a discrete math 2 class over
We
the
don't.
summer or something.